In the last lecture, we were discussing the conservation equation in a spherical coordinate system. A spherical coordinate system where one of the coordinates is the distance from the origin r. Distance from the origin is square root of x square plus y square plus z square. Okay. So, that is the radial coordinate, the distance from the origin r, and then two other coordinates are angles. The angle made by the displacement vector with respect to the z direction, okay, the angle made by the displacement vector with respect to the z direction is called theta. On the plus z axis, theta is equal to 0. On the minus z axis, theta is equal to pi, and on the xy plane, theta is equal to pi by 2. The third angle is the angle made by the projection of the position vector with respect to the x axis, that is called the meridional angle phi. Okay. That is called the meridional angle phi. So, the z coordinate is equal to r cos theta. Okay. The projection is r sin theta. Okay. Therefore, the x coordinate is r sin theta cos phi, and the y coordinate is r sin theta sin phi for this coordinate system. And it also explained to you how r is related to x, y and z. It is just the distance from the origin. Okay. Cos theta is z by r, or tan theta is equal to z by this projection onto the xy plane, that is square root of x square plus y square, and tan phi is equal to y by x. Okay. So, those are the relations between the r theta phi system and the x y z system. And I had explained to you that the theta and phi coordinates are very similar to the geographic latitude and longitude. Okay. If you recall, for the geographic coordinate system, the north and south pole are at plus pi by 2 and minus pi by 2, and the equator is at 0 geographic coordinate. Okay. So, therefore, this angle theta is just equal to pi by 2 minus of phi. Okay. It is equal to 0 on the north pole, it is pi on the south pole, and pi by 2 on the equator. The meridional angle is exactly the same as the meridian in a geographic coordinate system, where 0 meridian corresponds to the x axis. So, that the angle is determined is the angle between the location on the surface of the sphere and the x axis or the 0 meridian. Okay. And r is of course positive, okay, because it is a distance from the surface. Theta varies between 0 and pi. Okay. 0 is the north pole, pi is the south pole, and phi varies between 0 and 2 pi. Now, we were constructing a differential volume in the spherical coordinate system. Okay. The differential volume has to be constructed between 6 surfaces, 2 each that are perpendicular to each of the 3 coordinates, separated by a differential displacement in those directions. Okay. So, that is how we have to construct the differential volume in the r theta phi coordinate system. Okay. So, there are 2 surfaces that are perpendicular to the r direction. Before I proceed, let me just also show you what are the unit vectors in this case. Okay. In this case, the unit vectors are vectors in the direction of increasing coordinate, okay, which means that the unit vector in the r direction ER is in the direction of increasing r. Okay. Unit vector in the r direction is in the direction of increasing r. Unit vector in the theta direction, okay, is in the direction of increasing theta. Okay. The angle theta increases as the angle with the z axis increases, and therefore, the direction of the theta coordinate is in the theta coordinate is in the direction of increasing theta, okay. And the phi coordinate is in the direction of increasing phi, okay, perpendicular to this, okay. Okay. And these three form an orthogonal coordinate system. The direction of increasing r is perpendicular to the direction of increasing theta, and the two are perpendicular to the direction of increasing phi. So, this is an orthogonal coordinate system in which the three unit vectors are perpendicular to each other at all points in space. In contrast to the Cartesian coordinate system, the unit vectors are not independent of position. Okay. If I took another position, for example, here, okay, I took another position here, for example, the ER coordinate will be in this direction, okay, the radial coordinate will be in this direction. Okay. And you can see that it is different from the radial coordinate here. Okay. It is directed along the unit vector from the origin, which is different at the two locations. Okay. So, therefore, the radial coordinate does change as the position changes. The theta coordinate will also change as the position changes, and the phi coordinate also will change in general as the position changes. However, at each location, the three unit vectors ER, E theta and E phi are all perpendicular to each other at all points in space. Okay. Okay, the three of them are perpendicular to each other, even though the directions of those unit vectors change as position changes in this three-dimensional coordinate system. Okay, so, let us construct a differential volume bounded by 6 surfaces, so that we can do a balance of mass in, mass out and the source within that volume. Okay. So, if this is the surface at r theta phi, okay, so this is the point r theta phi. Okay. The surfaces perpendicular to the r coordinate, as I said, are spherical surfaces. Okay. Are spherical surfaces. The surface at r okay, the surface at r minus delta r by 2 and r plus delta r by 2, okay, and this displacement is delta r. Okay. Those are the two surfaces that are perpendicular to the r direction. Okay. So, if I expand that out here, this is delta r, okay, and this is the surface at r minus delta r by 2 and r plus delta r by 2. Okay. Those are the two surfaces perpendicular to the r direction. Okay. There are two surfaces that are perpendicular to the theta direction, okay, and that is this surface and this surface. Okay. So, if this angle is theta, okay, then I have two surfaces, okay, this one and this one, which are surfaces of constant theta, okay, perpendicular to the direction of E theta, okay, here perpendicular to the E theta direction here, two surfaces that are perpendicular to E theta. Okay. And these surfaces, okay, are, okay, so this is at theta minus delta theta by 2. theta plus delta theta by 2. And what is this distance between these two surfaces? Okay. This distance between these two surfaces, it is not delta theta. Delta theta is the increment in the angle, and the angle is dimensionless. Okay. So, this increment is not the increment in the angle, because the angle is dimensionless. This is equal to r times delta theta, okay, because the distance you travel on a circle is equal to the angle in radians times the radius. Okay. The distance travelled is the angle in radians times the radius. So, this is equal to r times delta theta. Okay. And then there is an increment in the phi direction here, okay, the phi direction here between the locations phi minus delta phi by 2 and phi plus delta phi by 2. Okay. So, this, okay, so if I draw it, this looks something like this. Okay. The distance moved in the phi direction. When you increase the angle phi from phi minus delta phi by 2 to phi plus delta phi by 2. Okay. The angle moved is delta phi. Okay. The angle that you travel when you go from phi minus delta phi by 2 to phi plus delta phi by 2, that angle is phi. The distance moved is not delta phi, okay, because delta phi is an angle. The distance moved is the distance from the center of rotation times the angle, okay, and the distance from the center of rotation is r sin theta. Okay. The projection onto the xy plane is the distance, the center of rotation, okay, for the angle phi, and therefore, this distance is equal to r sin theta delta phi. Okay. So, this is the cubic volume. Okay. This is the this is the 3-dimensional differential volume bounded by two surfaces in each coordinate. Surfaces at r minus delta r by 2 and r plus delta r by 2. Distance between these two is delta r. Surfaces at theta minus delta theta by 2 and theta plus delta theta by 2, okay, separated by a distance r delta theta in the e theta direction, and the two surfaces at phi minus delta phi by 2 and phi plus delta phi by 2, separated by a distance r sin theta delta phi, okay, in the phi direction. Okay. So, therefore, the increment in the coordinates is equal to delta r delta theta delta phi. Okay. And now, the distance travelled is equal to delta r delta theta, r sin theta delta phi. That is the distance travelled in the 3 coordinate directions. Okay. And this is also written as, okay, h r delta r, h theta delta theta, h phi delta phi. Okay. Where h r, h theta and h phi are what are called the scale factors. They are the factors which are used to convert the increment in the coordinate to the actual distance travelled. Okay. In this particular case, for a spherical coordinate system, h r is equal to 1, because delta r is equal to the distance travelled. H theta is equal to r, okay, because the increment in theta delta theta, okay, the increment delta theta times the scale factor is the actual distance travelled, and the scale factor h phi is equal to r sin theta, okay, because the distance travelled when phi is incremented by delta phi, the distance travelled is r sin theta delta phi. Okay. Yeah. So, now we have this coordinate system and we have this differential volume, and we have to identify the surfaces and then do a balance for these surfaces. Okay. So, let us identify the surfaces. Okay. Okay, so, the location of the surface perpendicular to, or let me just say, okay, I will just give you the surface area of each of these surfaces. Okay. The surface at, okay, so let me just draw for you once again what is the differential volume. So, these are the 6 surfaces of the differential volume. Okay. So, let me just show. So, this is the differential volume. Okay. So, the distances are, okay, r delta theta here, delta r in this coordination, in this direction, in the r direction, and r sin theta delta phi. Okay. So, what are the surface areas of these surfaces? Okay. So, surface at r minus delta r by 2. Okay. What is the surface area of the surface at r minus delta r by 2? This is going to be equal to the 2 incremental distances perpendicular to the surface. Okay. That is the product of those 2 incremental distances perpendicular to the surface is going to be the surface area. Okay. The 2 incremental surfaces perpendicular to the r direction are h theta sin theta into h theta delta theta into h phi delta phi, okay, at r minus delta r by 2. Okay. Those are the two displacements perpendicular to the coordinate direction at the surface at r minus delta r by 2. Okay. Note that h theta, okay, if you recall, I told you that h theta was equal to r and h phi was equal to r sin theta. Okay. So, h theta and h phi do actually depend upon r, okay, and that has to be taken into account in this calculation. Okay. Surface at r plus delta r by 2 is going to be h theta delta theta h phi delta phi at r plus delta r by 2. Okay. So, two surfaces at r minus delta r by 2 and r plus delta r by 2 about this location r theta phi. Okay. Then I have the surface at theta minus delta theta by 2. Okay. Product of the two perpendicular incremental displacements perpendicular to the theta direction is h r delta r into h phi delta phi at theta minus delta theta by 2, okay, at that location. Okay. Note that I told you that h phi was equal to r sin theta. Okay. Therefore, this increment actually depends upon theta in this case. Okay. Similarly, the surface at theta plus delta theta by 2 is h r delta r h phi delta phi at theta plus delta theta by 2. Okay. Those are the two surfaces perpendicular to the theta direction. Okay. And then I have two surfaces perpendicular to the phi direction, that is surface at phi minus delta phi by 2 is h r delta r h theta delta theta at phi minus delta phi by 2. And the surface at phi plus delta phi by 2 is h r delta r h theta delta theta at phi plus delta phi by 2. Okay. So, those are the 6 bounding surfaces of this differential volume, and the volume itself is going to be equal to h r delta r h theta delta theta h phi delta phi. Okay. So, those are the surfaces surrounding this differential volume and the volume itself, for which we have to write the balance equation. Okay. And the balance equation is the same as that we had for before. Okay. Change in mass in time delta t is equal to mass in minus mass out plus the production. And we have to evaluate each of these terms separately. Okay. First one, this is equal to the mass density, the change in the mass density times the volume. The volume is h r delta r h theta delta theta h phi delta phi into the concentration at r theta phi t plus delta t minus the concentration at r theta phi t. Okay. There is the change in mass in a time delta t, the change in the concentration times the volume, and the volume is given by h r delta r, h theta delta theta, and h phi delta phi. Okay. Mass n at r minus delta r by 2. Okay. What is the mass coming in at the surface at r minus delta r by 2? There is a mass coming in at this surface, okay, at the inner surface. What is the mass coming in within a time delta t is going to be equal to the flux, okay, times the surface area. The surface area of the surface at r minus delta r by 2 is going to be equal to the two perpendicular distances, okay, the whole thing at r minus delta r by 2 times delta t. Okay. The flux in the r direction, okay, at the surface at r minus delta r by 2, as you can see, a flux in the positive r direction results in mass entering the differential volume. Okay, results in mass entering the differential volume. Therefore, the mass input within a time delta t is the flux times the surface area times delta t, and the flux is the product of these two, okay, okay, perpendicular, okay, coordinates, that is the surface area. The two perpendicular coordinates r delta theta and r sin theta delta phi, or h theta delta theta and h phi delta phi. Okay. When there is mass out at r plus delta r by 2. Okay. There is mass out at the surface at r plus delta r by 2 if the flux is positive. Okay. There is a mass out at the surface at r plus delta r by 2 if the flux is positive, and that is going to be equal to j r into the surface area h theta delta theta h phi delta phi at r plus delta r by 2 times delta t. Okay. That is the mass out. Note that h theta and h phi do depend upon r. Okay. So, therefore, they will be different at the inner and the outer surfaces. Okay. Similarly, there is mass in at theta minus delta theta by 2. Okay. This is going to be the mass that is coming in at the surface at theta minus delta theta by 2, okay, in the theta direction. There is mass out at theta plus delta theta by 2. Okay. There is mass coming in at theta minus delta theta by 2 and mass out at the theta plus delta theta by 2. Okay. And these are equal to j theta into h r delta r h phi delta phi. The flux in the theta direction times the two perpendicular displacement h r delta r and h phi delta phi times delta t. Similarly, there is mass out j theta h r and there are two further contributions to the flux from the surface. Mass in at phi plus phi. The flux in that direction j phi times h r delta r plus times my apologies, this should be h theta delta theta. Okay. The increment in the two directions perpendicular to the phi direction is the surface area perpendicular to the phi direction. Okay, so this h theta delta theta. And once again, this is phi minus so these are the mass in and mass out at the surfaces and the change in mass in a time delta t. Okay. I have to add one more term here, which is due to the source or sink, that we will do in the next lecture, and we will go ahead and derive the conservation equation for the concentration in a spherical coordinate system. So, I will continue this in the next lecture. I will see you then.